Welcome to This Explainer. Look, we're gathering today for what is basically a masterclass on the absolute ultimate engineering test of our era. We're going to unpack the science, the raw data, and the physical realities of our changing planet. But more importantly, we're going to look at how we actually build for it. As students of engineering, science, or just as naturally curious learners, you are literally the architects of tomorrow. You're the ones who are going to have to build these solutions. So let's tackle this whole thing step by step.
Okay, you've definitely seen pictures like this before. On the left, we've got the natural abundance we all know, right? Life, possibility, perfect balance. And on the right, well, that's the cracked, arid future we are actively heading toward if we don't pivot and fast. Now, the goal here isn't to scare you or overwhelm you with this stark contrast. The goal is to empower you with the facts, because as we know, truly understanding a problem is the very first step in engineering its solution.
So here's our academic roadmap for today. We'll be decoding our changing climate, looking at the greenhouse energy balance, and examining climate-forcing mechanisms. Then we'll dive into evidence from nature's archives, explore the global domino effect, and finally, tackle the engineering challenge itself. Let's jump right in. Section 1. Decoding our changing climate. Establishing the baseline. Let's start right at the absolute fundamentals. What is the actual difference between weather and climate? I like to think of weather as your mood on any given day. It's short term. It's the day-to-day condition of the atmosphere. It's raining today or it's super hot outside right now. Climate, on the other hand, is the long-term average of those weather patterns in a specific place, usually calculated over 30 years or more. So if weather is your mood, climate is your whole personality over a lifetime. Climate change, then, is a massive shift in those long-term historical averages. And right now, the Earth is heating up faster, on average, than at any time in the last 2,000 years. Which brings us to two terms people mix up all the time. Global warming is simply the long-term increase in Earth's average surface temperature. Think of it as the symptom. Climate change, however, is the broader disease. It completely encompasses that warming, sure, but it also includes all the cascading physical effects. We're talking melting glaciers, rising sea levels, entirely shifting seasons, and ecosystem collapse. When we say climate change, we are talking about the entire package of physical alterations happening to our planet right now. Moving on to Section 2, the greenhouse energy balance, Earth's invisible blanket. Take a look at this specific number here, 33 degrees Celsius. I want you to imagine the Earth wrapped in this delicate, totally invisible atmospheric blanket. Certain gases in this blanket, greenhouse gases like carbon dioxide and methane, they trap heat from the sun. Now, this natural greenhouse effect is actually a really good thing. It's essential. Without it, our planet wouldn't be this lush, vibrant world. It would literally be a frozen, uninhabitable wasteland roughly 33 degrees Celsius colder than it is today. But the systemic failure begins when we start messing with the thickness of that blanket. Ever since the Industrial Revolution back in the 1800s, human activity has rapidly altered our atmospheric composition. We're burning just massive amounts of fossil fuels, coal, oil, and gas for electricity and transport. We're engaging in widespread deforestation, literally cutting down the very trees that act as natural carbon sinks to absorb CO2. And on top of that, our agricultural practices, especially livestock and rice farming, release immense amounts of methane. Basically, we are artificially thickening the blanket, trapping all this excess heat, and completely throwing a very delicate thermal equilibrium way out of balance. All right, Section 3. Climate forcing mechanisms, the invisible game. So think of climate forcings as the buttons that push the Earth's climate in one direction or the other. Now, natural forcings have been around for millions of years. Say, a massive volcano erupts. It acts like a giant mirror, reflecting sunlight and temporarily cooling the Earth. We also have solar cycles that naturally fluctuate. And Milankovitch cycles, which are changes in Earth's orbit and axis tilt, those actually drive ice ages over tens of thousands of years. But contrast that natural rhythm with human-caused or anthropogenic forcings. These involve greenhouse gases that are currently sitting at 800,000-year highs alongside massive land use changes. The absolute crucial point here is the timescale. Natural forcings, they usually take centuries or millennia. Human-caused forcings are altering the planet in mere decades. It's the sheer speed of this change that is just structurally terrifying. Let's look at Section 4, evidence from nature's archives. How do we know? This brings up the ultimate critical thinking question, right? How do scientists actually know this is real? How do we measure ancient climates if literally nobody was around to look at a thermometer 100,000 years ago? Well, the answer brilliantly illustrates the sheer ingenuity of science. We use something called proxy data. These are indirect clues that basically act as nature's historical archives. Step 1. Scientists go out and drill deep into the ice sheets of Greenland and Antarctica to extract these massive ice cores. The compacted layers of ice in these cores contain tiny trapped bubbles of ancient air. That allows us to directly measure historic CO2 levels and temperatures. It's like a time machine. Step 2 is dendrochronology. By studying the thickness of tree rings, we can reconstruct climate patterns going back thousands of years. Step 3 involves reviewing historical records, like old medieval harvest diaries. And Step 4 looks at glacial geology and mapping ancient sea levels. And here's the kicker. Every single one of these independent archives tells the exact same story. The speed of our current warming is entirely unprecedented.
Which leads us to Section 5, the global domino effect, cascading consequences.
Right now, the global average temperature is about 1.44 degrees Celsius warmer today than it was in the late 1800s. Now, a degree and a half, that might not sound statistically significant to the untrained ear, but let's really contextualize that severity for a second. During the last ice age, when massive parts of North America and Europe were literally buried under miles of solid ice, the global average temperature was only about 4 degrees Celsius cooler than it is today. Let that sink in. A shift of just 1 or 2 degrees dynamically, fundamentally alters the entire Earth system. And that thermal increase, it triggers massive, interconnected chain reactions. It's a real domino effect. Ice sheets melt, adding huge volume to the oceans and raising sea levels. And because a hotter atmosphere naturally holds more energy and moisture, we're seeing an intense increase in extreme weather, heavier floods in some regions, prolonged, devastating droughts in others. Ecosystems that simply cannot adapt fast enough are facing major disruption and mass extinctions. And look, we absolutely must acknowledge the human variable here. The poorest nations, the ones who have contributed the absolute least to this greenhouse blanket, they are the ones facing the most disproportionate suffering. This is just as much an urgent issue of climate justice as it is of atmospheric physics.
Finally, Section 6, the engineering challenge. This is your story.
Here is the reality check. Our current global infrastructure was designed using historical weather data for a climate that simply no longer exists. History is no longer a reliable guide for engineering design. Consider some real-world systemic failures we're already seeing. Take thermal buckling, for example. Steel expands in heat, right? Well, in 2023 alone, the U.S. recorded over 600 rail buckling events caused by extreme heat. That leads to derailments and massive economic damage. Next, look at unprecedented moisture loads. A hotter atmosphere holds way more moisture, which leads to unprecedented ice and rain accumulation that our power lines and structural supports just weren't engineered to carry. And then there's extreme thermal gradients, where different parts of a structure expand at totally different rates because of intense heat waves. That's causing premature cracking and serious defects in our concrete bridges. The traditional assumptions we've relied on are fatally failing under the stress of these new extremes. But here is where we shift the narrative from anxiety to absolute empowerment. Because the truth is, we already know many of the solutions. We need a totally new generation of minds to design green infrastructure, cities that work symbiotically with nature using things like permeable pavements and constructed wetlands. We need engineers to step up and build massive, intelligent, renewable energy grids to harness and store clean energy. We have to start designing for climate resilience, meaning infrastructure that is mathematically robust enough to bounce back from the extreme events we know for a fact are coming. And we must develop sustainable materials to replace carbon-intensive staples like traditional cement and steel. I want to leave you with this thought. The structures you reimagine and build today will determine our collective future. Thank you so much for joining me for this explainer. As you step out into your city tomorrow, I want you to look around and ask yourself, is the infrastructure around you built for the climate of the past or the climate of our future?